Hello everyone and welcome to this Copernicus Marine Service practical session about sea ice observations in the Arctic. My name is Sylvain. I'm a scientific engineer at NOVELTIS and I will be your trainer during this session. Today you will use a Jupyter Notebook to have a comparison between sea ice observations and model outputs. You will also have a closer look at CMEMS products, their structure, format, variable, and how to explore and plot them. Before starting, I have two general notes about Jupyter Notebooks. A notebook is composed of different cells, and some of them have code inside of them, which you have to run in order to execute the code. To run a cell, you have two options. Either you select a cell and press this button, which runs the selected cells and advance, or you use a keyboard shortcut, Shift plus Enter. Besides, if, for any reason, the kernel is not working anymore, you can press this button in the top menu, which restarts the kernel. Then, on the top menu, click on Run, and select cells you want to run before, and run all above selected cells, and it will execute all the cells you have already gone through. So today, during this session, we will have a closer look at the data, the different model satellite observation products. After exploring the netcdf file content of the product, we will go through two exercises. The first one will help you map the data at a given time, and the second one will have a comparison of sea ice fractions between model and observation. As you may know, the Arctic covers a vast area, most of it being uninhabited. The human infrastructures there are scarce, and they are certainly not spread enough to monitor precisely this rapidly changing environment. A previous notebook on CMEMS physical model products highlighted the great seasonal and annual variation of sea ice state parameters in this region. You can access this notebook just pressing this link. As the region is warming up twice as fast as the rest of the world, it requires a more intense monitoring. Models also need reliable observation as inputs to provide the most accurate estimations. This is where space-based technologies have a key role to play. They constitute a powerful tool to observe this particularly remote area on a daily basis. This notebook introduces you to the manipulation of the CMEMS sea ice observation products and how they compare to the model products. In this notebook, you will learn how to handle and explore netcdf files and how to map and compare sea ice fractions. First, let's have a look on the data. The model product we will be using during this session are further described in a previous notebook on CMEMS physical model products and on the CMEMS website. Today we will focus on sea ice concentration charts in the Arctic oceans. The operational sea ice services at Met Norway and DMI provide ice charts of the Arctic area covering Baffin Bay, Greenland Sea, Fram Strait and Barents Sea. The charts show the ice concentration. The three different types of ice charts, which we will call datasets in the future, are produced from twice to several times a week. MetNode charts are produced every weekday, whereas DMI regional charts are produced daily at irregular interval, and a supplemental DMI overview chart is produced twice weekly. For each dataset you can have an overview giving the geographical coverage, the variables here, sea ice area fraction, spatial coverage, and temporal coverage, for example. In particular, as explained above, today we will use three different products: MetNo with a spatial coverage available from January 2018 until now and produced daily, DMI charts with a different area coverage available from the same time and produced daily but at irregular intervals, and the DMI overview produced twice a week. If you want to get more info on the observation products, you can find more information and access the download service in the dedicated product page on Copernicus Marine Service web portal. You can have more information about the product itself in the product user manual and information about the quality of the product in the quality information document. The product used throughout this notebook have been downloaded ahead of the training session for you, and they are stored in the data folder. If you want to access it, here you have the data folder with the datasets. If you wish to download the data yourself, please be sure to have CMEMS user credential. Otherwise, you can get them with this link. Moreover, here you have the parameter used to download each dataset from the CMEMS portal, giving you the dimension and what we are looking for in this product. Monthly means for MetNo, model product, twice a week for DMI. Just a tip, if you need a guidance about the different services for downloading CMEMS products, please check. During this training, we are going to use Python programming language in order to explore the datasets. But first, the notebook must be set up with all the necessary tools available from the Jupyter Notebook ecosystem. We have to import 5 different modules for our training. The first one is the OS module. It is the operating system interface in order to manage paths, create directories, for instance. NumPy allows carrying out scientific computing with Python and managing arrays. Xarray handles netcdf files in an intuitive and interactive way. Matplotlib is a Python numerical plotting library, and the basemap toolkit is a library for plotting 2D data maps. The following cells import those libraries and import a 6th one as well, which is warning, in order to filter the different warnings which could be raised during the execution of the code. So in order to execute this code, I click on the cell, and I could either click on run the selected cell and advance, or use the keyboard shortcut Shift plus Enter. You can see that this is the first cell that I execute, and you could see a little star at the beginning when it was running, but while it displays a number, it's finished. So we have imported all the modules we need for this training. Those requested Python libraries have been installed on the CMEMS Jupyter Hub ahead of this training session. Hence, no installation is needed during this session. If you wish to replace this notebook later on your own infrastructure, you may need to check your Python version and install the Python library used in this notebook. The following part gives you hints on setting up the appropriate environment for this notebook to run smoothly. First, the Python version. For this training, we need Python in version 3.7. To check it out, you can use this command, Python version. You will note that there is exclamation mark before. It is to run a shell or Linux command in the notebook. So my Python version is 3.7.3. It's okay. If needed, you can install the right Python version in this way using the command conda install python equals 3.7. If you are using the standard Anaconda 3 installation, you can install the needed modules executing the following command in a new cell. Conda install NumPy, Xarray, Matplotlib, basemap, netcdf4, basemap data hires. Then it will ask you to restart the kernel, and please do so. The kernels maintain the state of the notebook computation. You can reset this state by restarting the kernel. This is done by clicking on this. Now that the notebook is set up, we can explore the netcdf file content and our datasets. We are going to work with the observation product over the Arctic Ocean with sea ice concentration charts, and we are going to use the DMI overview files to get started with Python features. To start, we will define two variables, which are the root path, which is the path pointing to the data directory, and the name of the netcdf file, which is composed of the root path and the name of the file itself. So, as I said before, we have downloaded the data in the data folder, which you can access here, and our file is called this way. So I just define those two, pressing Shift plus Enter as before, and now we have told Jupyter with data are going to work with and where it is, so we need now to open the data. The following cells open the netcdf file with the Open Dataset command, and it allows you to interactively browse the content of the file. Let's see what it does. Now we can explore these datasets. We can see that it's of dimension 2232 by 2413 with 94 time iteration, the coordinates of the datasets and data variables and its attributes. We can access the attributes of a variable by clicking on the Show Hide Attribute button, which is this one. For ice concentration, we have a long name, standard name, the units, grid mapping, source, and you can access the data representation by clicking the Show Hide Data Representation button. So we see that we have quite a high number of values of type float32. We can also explore the attributes. So we have a title, convention, creation, produce dates, some comments, and sensor, and everything you need to know about the product. Now we need to store the file content into an X-array dataset, and we would like to print the content of these datasets. So we need to execute the following cell. This line open the netcdf file with XR open datasets, and handling the netcdf file, and we are going to show the header with the global attributes of these datasets. And you can see we have same information: attributes, data variables, coordinate, dimension. A netcdf file is a common way of storing scientific data. It contains the dimensions, which we have here, several variables depending on one or more of these dimensions, the ice concentration, which depends on the time, on the latitude and longitude. We have several general information about the product, which are called global attributes. We have already explored them, so we have comments, producing dates, title, everything which are part of the header and metadata of the product. We could store one attribute in a variable, for example, the institution. Here we can see that it was a DMI who produced this product. Let's see how to get it. So from my dataset, I use this ATTRS and naming the attribute I want to explore, which is indeed DMI, as we could already see. We can print the different variables of a netcdf file using data_vars, and we have ice concentration and CRS. So this function displays all the available variables in one product along with the dimensions that depend and their data type. Float 32 here, meaning that each value is a float coded on 32 bits. You can see that the present variables in the files depend on several coordinates. To get information about these coordinates, we're just going to look at those coordinates in the netcdf files. So we have longitude, latitude, time, YC and XC. You can print the dimension of the netcdf files, which we already saw before. And if you want to store the values of a variable in an array, you can have variables point the values, so the variable name. If you want to have the time variable, you just change variable here by time, so you get the values of the time variable in our dataset. Here nothing is displayed because we are only storing the values in a variable. If you want to check the content of this array, you just have to use the function print and then the name of the variable. Let's see what's inside. And we have all the time of the product. So you can see that the dataset contains variables values twice a week for each week from January to November 2019. So the 2nd, 6th, so there are 4 days, 3 days, 4 days, 3 days. So we have data twice a week for 11 months. Another way of displaying raw information about the netcdf file is to use a Linux command, which is ncdump. The H parameter here allows you to have access to the header only of the netcdf file. So as we saw before with Python version, when calling a Linux command from a notebook, you have to insert an exclamation mark at the beginning of the command line. So here, let's have a look on the header of the file. And you find similar information. However, it's not as readable as it was with the dataset open in Python, because it displayed the same kind of information, but the command line shows that the time variable is stored in seconds since 1981, which is not easily readable by a human. Here you can see it. Whereas when we open the datasets with Python and Xarray, it conveniently interprets the time coordinate as a date in year, month, day, hour, minute, second when ingesting the product, which is easier. Now that you have learned how to open and manipulate a netcdf file, it would be nice to visualize the content of the product onto a map. The variable of interest in the studied dataset are geographical variable. During this first exercise, you will learn how to map the sea ice fraction in winter and summer. In this exercise, we will have a closer look at the sea ice concentration. As we have seen before, there are two variables in the dataset, and we have to define the name of the variable of interest in the netcdf file. So, first, we define again the path of the file to open, the physical model file name, and just print it to see the path of the netcdf file. We are then going to open the dataset and show the content of the variable fin. So as we've seen before, we have a dataset of dimension 94 in terms of time and geographical coordinates more than 2000. There are two data variables, ice concentration and CRS. The one we are interested in is ice concentration, so we define the name of the variable of interest for the exercise, ice concentration. Then we have to open and store the file variable of interest. In order to plot the variable of interest, we'll need the time coordinate, but also the latitude and longitude coordinates and variables. This is the purpose of this cell. So let's first store the variable of interest, which is a sea ice concentration, in individual arrays. This command gets a variable var name in the dataset and associated coordinates and attributes in this var. Then we define latitude and longitude in a variable, getting the latitude from the dataset and the longitude from the dataset, and the time. In order to spare some memory in our notebook, we have to close the dataset, because it's not useful anymore, because we have all what we need: the variable, latitude, longitude, and time. Let's close it. As we have seen before, the dataset contains sea ice concentration values twice a week for the whole 2019 year. In this exercise, we will only plot the variable of interest for 2 dates, March the 10th and August the 11th. But you can try plotting different dates after the exercise if you want. First, we have to prepare the data to be plotted. We need to define the variable of interest and the dates to plot with a format which is compatible with the time variable. So we define the dates to plot with a format year, month, day, t, hour, minute, seconds. First plot on March the 10th and second plot on August the 11th. And we extract data corresponding to those dates. The date selection and print the comment of the resulting data arrays is done with this command. So we, in the var variable, we select the corresponding date and the closest one, and we print it. And then we select the second one. So selected one, we were selecting the closest one in time, because we set there at midnight, but the closest one was at midday. So we have correctly selected the date on March 10th and August 11th, and the dimension of variables is yc and xc. The two variables var date1 and var date2 now respectively only contain the var name variables for the selected dates. If you want to select a date that is not in the dataset, then this function selects the nearest date in the data array. You can also note that the var name variable does not depend on the time dimension anymore. As there was only one remaining date per dataset, the selection method automatically removes the time dependency of the name variable. Here, there is no time dependency. As with earlier, the open dataset functions interpret the time variable as a date. The precision of this date is too high, and we are looking up monthly average value, because the precision is at nanosecond. It would be more practical to work with date format of the type year, month, and day. To do so, we can use a changing date format, which is as type, considers this value as type of date times 64 unit function, and this will set in the below cell. We will use day, d, as a time unit here. If for your application you need other units, you can use them as well. So you can use y for the year, m for the month, weeks, but also for hours, minutes, seconds, and milliseconds. So for the first date, we use a value of the time variable of var date1 as day only, and we print it, and same things for second date. Now you can see that initially the value was precise down to nanosecond, but now it's only precise to the day, and that's quite enough for us. Then we are going to plot the data. For this, we use subplot functions from the matplotlib module in order to plot the data for both dates on the same figure, with one subplot per figure. A subplot is called an X, and each X probably can be defined independently. For plotting over the Arctic, we will use a base map NP-steer projection, which is in the North Polar stereographic projection and corresponds to the stereographic projection used in the product, which you can access in the header of the product if you want to check it. We also define the following parameters: the center of the desired map domain, the axis on which to create the base map instance, the bounding latitudes for pole-centered projection. These projections are square region center on the north or south pole. The center of desired map domain longitude is at 6 o'clock, and the latitude circle bounding lat is tangent to the edge of the map at longitude 0. And the final one is a resolution of boundary database to use. If you want, you can play around with these parameters later and see how it affects the map. The function pcolorMesh from the matplotlib libraries will allow us to create a pseudo-color plot with rectangular grid. So, in this cell, we create a subplot of 1 line and 2 columns, defining the size of the figure, 16 inches in width and 8 in height. Then we plot the first date in the first subplot, creating the base map with the correct projection, center of desired map domain, bounding latitude and resolution. Then we add coastline, country boundaries, and fill continents. We then draw the parallels and meridians. Meridians are created between 30 and 360 degrees with intervals of 60 degrees, and parallels are created between 60 and 90 degrees with intervals of 5 degrees. Then we create the first date with the pcolorMesh function, adding the color bar and a specific title for this plot, which is a DMI sea ice coverage. At the date 1. Then we can plot the second date, creating a second base map, drawing the coastlines, drawing the meridians and parallels, and plotting the second date, adding the color bar and the second title. We can save the file in the out folder, which you can access here, with a specific name, and we're going to print the name of this file and showing this figure. It can take quite some time, but here are the results. So we have the file which is saved in the out folder, and we have the two maps for the two dates on March 10th and August 11th. We can see quite a difference in the sea ice coverage. In March, there is an important part of this area which is covered in ice, nearly with 100%, whereas in August the sea ice has melted and disappeared, only on the northest part of this region. We just generated two maps of the sea ice coverage from the DMI product for March and August 2019. Both maps highlight the variability of the sea ice extent over the year. You can see that the geographic coverage of this product is limited to the Greenland coastal waters. If you want to repeat this analysis for different dates, you can change the date plot in section 531, which is here. You can change date plots if you wish. This will give you different results, but you can choose precise date you want to plot. During the first exercise, we compare the same product but on different dates. Now, let's compare monthly means of sea ice fraction but between the different products on the same date. This is the goal of this second exercise. First of all, we will plot and compare for January to November 2019 the model product and the DMI overview. Then, we will plot and compare in August 2019 the model product, the DMI overview, and the METNO product. To have the comparison from January to November 2019, we first need to select a netcdf file and the variable name. It is same as before. We define the root path to data, the fname model, which is a root path plus dataset name, and the observation file, which is a DMI dataset. We are looking for the FICE variable name, which is a sea ice fraction, and in the model, and the ice concentration in the observation. We open the netcdf file with XR open datasets for the model and observation, and we store them in fin model, fin observation. And then we create an output directory to save the plot in the out directory. This is done. Now we can open and store the file variables of interest. We will need the time coordinates in order to plot the variable of interest, but also latitude and longitude coordinates, and the sea ice fraction variable for both model and observation products. We already stored the time coordinate in var time previously in exercise 1, and we are going to do it again in the following cells for the model and observation. So, from the dataset, you get the variable names, and we store the variable of interest. This is done. And now we are going to store the content of latitude, longitude for both model and observation. So from the dataset we are looking for the latitude variable and longitude variable, and same for the observations. Then, in order to spare some memory, we are going to close the two datasets. We have seen before, when we explore the netcdf file, that DMI model product contains twice a week mean value of sea ice concentrations. Here we can have the time values, and we can see that it's twice a week, every 4 3 days at midday. To compare the observation to the model value, they need to be on the same temporal resolution. So we have to resample the observation product down to a monthly mean, because the model product is on this time coverage. To compute the monthly average out of weekly values, we are going to use a resample function. It returned a resampled object. It handles both downsampling and upsampling. The resampled dimension must be a datetime-like coordinate. Here we will generate a monthly mean by using the argument time is equal to m for months. So we're resampling the variable of the observation to the months, and we take its mean. It takes quite some time to compute it. And now let's check the new time dimension of the observation variable. As we expected, we obtain a dataset with 11 monthly means time frames, as the original dataset spanned from January to November. So we start in January and we go up to November. So now our observation and model have the same temporal resolution. We can compare them now. We are now going to generate, show, and save the plots. We are going to generate a figure with 2 columns of 11 rows. So there is 1 row per month, and 1 column for the observation, and 1 column for the model. The sea ice concentration maps generated from the model product are displayed on the axis with even indices, which will be the right column, and the one generated from the observation product will be displayed with odd indices on the left column. We first define the plotting window to center it on Greenland, and in order to automate the subplot generation, we're going to loop over the 11 dates. We create a figure of subplots with 11 rows, 2 columns defining the size of the figures, and converted the axis to a flattened 1D array for easier manipulation. Then, as said, we create a loop on the date to plot the data. So this gives the length of the observation time, the length of all the values of observation time. As before, we convert the time values to monthly values. We plot base map drawing coastlines, drawing countries, filling continents. We draw meridians and parallels, and we plot the variable with the same function as before, pcolor mesh, adding color bar on the right and the title. This was for the model, and we do the same for the observation. Then, after plotting all those data, we define the output name of the file, we print the name, save the file, and show it. This can take quite some time to compute. It took a few minutes to compute, but now we have all the figures. So 11 lines and 2 figures per line. On the left the model and the right is the observation. So starting in January we can see that there is a quite important sea ice fraction around Greenland, and as time passes and we go up to summer, ice is melting and sea ice fraction is reducing, all up to the summer when there is no more ice in the Baffin Bay here. And as summer ends, sea ice fraction increase again in those regions. What is interesting to note as well is that there is in general a very good agreement between the reanalysis of the model and the observation product. What is important to note is that the monthly observation sea ice fraction is an average of 8 or 9 values per month, because there were 2 weekly values. Let's now compare the different products on the same month, for instance in August 2019. So in this section we will explore the 2 products used in the previous section and add the METNO product, which was presented in the 2.2 section. We have already loaded the data from the DMI observation product, so we are not going to do it again in this section, but we will load the data from the METNO file. To do this, we select the netcdf file and variable name, so in the data folder with the file name of the dataset, we are interested in the ice concentration variable, and we open the dataset and store it in the FinOps2 variable. Then we have to open and store the file variable of interest. We will need the time coordinate, but also the latitude and longitude coordinate and the ice concentration variable for the second observation product. So we store the variable of interest in individual arrays, getting the variable varname FICEOps, which was defined before, which is ice concentration for the observation. And we store the content of latitude and longitude in 2 variables. And then, in order to spare some memory of our notebook, we close the dataset. We have all the data and variables we need, but we have still some manipulation to do on the data. As explained earlier, the MATLAB product is produced daily. We can see that plotting the different values of the time. So in the August month, it's from every day it is produced. It's produced on a daily basis. In order to compare MATLAB and DMI observation to the model values, they need to be on the same temporal resolution. So, like we did before, we have to compute the monthly average. We have already done it for the DMI product, and we are going to resample the MATLAB observation down to a monthly mean for the August month. So as before, we use a resample function using a month's time, and we take its mean over the time coverage we are looking for. If everything goes smoothly, we are just going to have one time value for the month of August, which is correct, we have only one. This is great. Now we can generate, show and save the plots. It is quite similar to what we did before. We are going first to plot with the two observation products and the model. So we are going to generate a figure with 3 columns, one per product type. So we have the model first, then the observation of the DMI product, and then the observation of the MATLAB product. We defined the plotting window to center of Greenland, we define the indices corresponding to August months, and we create a subplot figure with 1 line and 3 columns. We first plot the model with a base map, coastline, drawing the country and filling the continents, drawing parallels and meridians, and then we plot the variable using the piece color mesh with the value of latitude, longitude, latitude, the color we're going to use, and the min and max values which were defined previously. For each plot we are going to add the color bar as well. The same is done for the DMI observation and for the MATLAB observation, so this is the same code as before. And as well we are going to define an output name, printing it, saving the file, and showing the figure. So let's just run it. It's going to take quite some time as before, a few minutes. So we have a figure which were created and saved in the out folder. So on the left we have the CI fraction model, the DMI observation and the MATLAB observation for August 2019. We can see that in general there is a very good agreement between the reanalysis of the model and the observation product. So here we can see in those areas there is no sea ice, whereas on the north there is a quite important fraction. It is also important to notice that the MATLAB product has a different geographic hold than the DMI one. DMI one is centered on Greenland, so it's hard to compare them, notably in this region, in the Baffin Bay. So let's compare the model product to the MATLAB observation product on a more appropriate area. We are now only going to plot the second observation product and the model, changing the area of interest. Here we put different values for the base map to plot, so we will have a different area of interest. It is the same as before in terms of plotting, in terms of parameters, so I just run it and wait for it to plot the map. So you can see that the area displayed is different, and we have two lines, first one for the model and second one for the MetNob product. And now we can compare properly this product with a reanalysis model. It has a better resolution, we can see it in this area particularly, than the model product, and it provides information in the fjord where the model is not defined. You can see it here as well. In general, both models identify the same features. So in this area we have a greater sea ice fraction in this area as well, and the boundaries are quite similar. However, the model product has smoother transitions between sea ice coverage region. From here to here it's quite smooth, and whereas on the product we have a strong edge going from a full sea ice in this region to nearly nothing there. And the model product tends to underestimate its sea ice coverage, whereas the observation products show maximum values. You can see that in this area we have a maximum value for sea ice coverage with the MetNob product, here as well, whereas in the model product it's not maximal, it's around 0.9. So this is the end of this notebook and of this training about sea ice product and cements product. Thank you for your attention, and we hope you enjoyed this training on the physical Arctic model that are provided by Copernicus Marine Service for free, thanks to the European Commission. You can try to download new data and variables by yourself and visualize them, and you can try to make new maps and plots. You can also try other CMEMS products, which you can access here.